Hey everybody, welcome back to our continuing series solving some contest problems. This one was sent to me again by Bogdan Suchava immediately after the end of the Putnam competition this year. So that was just this last weekend, a little later than usual because of the pandemic. But didn't change the quality of the problems. If you don't know about the Putnam exam, it's typically held each year in December. And it is for undergraduate students across, well, generally North America. It is a remarkably difficult exam. So there are 12 problems that you're going to see over the course of 6 hours. You get 10 points possible per problem, so you can score up to 120 points. Very few people do. In fact, last year, the 2019 competition, I believe the median score was 2. So yeah, um, that's not a lot of points. So they do give out partial credit, but not a ton of it. The problems can be very, very tricky. They generally speaking get harder as you go along each section of the test. There's actually 2 sections, 6 problems on each. So when I received the problems, well, I decided, well, it's late at night. Let me just start with A1, which, in principle should be the easiest. So I sat down with my youngest son, Jacob. Yes, he was a huge, huge help. Anyhow, let's see if we can't try to suss out a solution to this. So this first problem, we're told that, well, there's going to be some positive integers, n, and we want to count how many of them there are, which satisfy 3 conditions. So the first condition is that it's divisible by 2020. Well, once you've seen enough Putnam exams, you know they're always going to have at least one, usually 2 or 3 problems that relate to the year. So going into the Putnam exam, like the very first thing you should do, right, when you start studying is find out cool properties of the year. And the first property you should always write down, I think, is the prime factorization. So in this case, 2020 is going to be 2 squared times 5 times 101. Okay, and once we know that this number n has to be divisible by 2020, we know it has to be divisible by each of these primes, at least, and even, if like 2 squared, right, it has to be divisible by 2 squared. So that's going to maybe tell us some things. We'll get back to that in a moment. Let's see what else we have. Also, n has to have at most 2020 digits. All right, so this condition is probably there just to make sure the answer to this question is not infinite. So it'll give us some sort of an upper bound. And then the third bit says the decimal digits of n are a string of consecutive ones followed by a string of consecutive zeros. So this means that our numbers look like 1, 1, 1, 1, 1, 1, followed by 0, 0, and then a bunch of zeros. Okay, and we don't know how many there are of each of these, but this is what the number has to look like. So those are the 3 conditions. It has to be divisible by 2020, which in particular means by all of these numbers. And also, it's not going to be more than 2020 digits long and has to be in this very specific form. All right, so it can't look like, for instance, 10,100, which would be 5 times 2020, because here there's a 0 in between these ones. Okay, so that one wouldn't work. So no bueno. Okay, so what can we do? Well, first observation based on the divisibility is it's definitely not going to end in a 1, right? There has to be at least 1 0 because it's an even number, right? And if it ended in a 1, that would be odd. So let's say we knew that there are m of these 1s and that there's little n of these zeros, then n has to be at least 1. Okay. On the other hand, we also know it's divisible by 2 squared, right, which is 4. Okay, well, what's the divisibility test for 4? So divisibility, we'll put a t in there, divisibility by 4. Well, the test is the last 2 digits must be divisible by 4. Okay, and well, a lot of times they teach this in school. It's actually not a very hard argument to make. Um, so probably the slickest way I can think to do it is to say, well, I know that every number, every positive integer, can be written as some number of hundreds plus some two-digit number. Okay, so here a could be any integer or positive integer. So a is any positive or maybe even non-negative, right? I mean, or sorry, not negative. It could be any non-negative integer. Maybe a is 0. Maybe it's just a two-digit number. And b lies in between 0 and 99. Okay, so if, for example, you had the number 34862, you can write this as 348 times 100 plus 62. Okay, so why is this relevant? Well, if you divide this number a times 100 plus b by 4, you know that 4 is going to go evenly into the a times 100 bit. And so the only thing left to check is, does a go into b? Okay, well, that's exactly what we're saying. You have to check the last two digits. All right, so that'll give you this. That's what this b is giving you, right? Is the last two digits. Okay, so what if our number then ended with 1, 0? So if we had something that looked like 1, 1, 1, 1, 1, and then a 0 on the end, well, now the last two digits are not divisible by 4. And so then the entire number won't be divisible by 4, and so the number won't be divisible by 2020. So actually, it's not just n at least 1, n actually has to be at least 2, right? There has to be 2 zeros on the end at the very least. Okay. What about this 5? Well, to be divisible by 5, you have to end in either a 0 or a 5. And of course, we know we're going to end in a 0. So this doesn't actually help us any. Okay, fine. How about 101? Well, maybe this one isn't as widely known in the sense that you don't usually get taught this in school. But it's actually a pretty easy one to work out. So divisibility by 101. Well, instead of writing down the rule exactly, let's just derive it. So instead of writing it in this more simplified version, let's try it this way. Let's start from, say, the constant. And just like with the divisibility by 4, we're going to do it 2 digits at a time. Right? It's not obvious at the start why we want to do that, but it's going to work out nicely. So let's call this like an A0. And then we're going to do A1 times 10 squared. And then we'll do an A2 times 10 to the 4th. Okay, so you can think about this as being 2 times 2. And then an A sub 3 times 10 to the 6, which again, you can think of as 2 times 3. Okay, and you keep going until, well, you have to stop because the number has gotten so big. You have an times 10 to the 2n. And so in each case here, we want that the A0, the A1, and so forth through AN are numbers between 0 and 99. And again, we don't really want A sub n to be 0. Okay, so again, we could take this number 34,862, and we can start by saying, okay, we take the first two digits at the end, you have 62, plus, then we have 48 times 10 squared, right? This is just 48 hundreds, plus 3 times 10 to the 4th. Okay, so that'll be 3 times 10,000. Hey, there you go, you got 30,000. Okay, so we can always do this with any positive number. Okay, now if we want to reduce this modulo 101, well, we make the following observation. 10 squared is equal to 100, and that is 1 less than 101. So modulo 101, this is the same as -1. Okay, so what if we do 10 to the 4th? Well, this is 10 squared squared. So this will just be congruent to -1 squared, or 1 modulo 101. Okay, what about 10 to the 6th? 10 to the 6th, that's 10 squared cubed. So that'll be -1 cubed, which is -1 modulo 101. Okay, so you see we get this alternating pattern, right? All of the odd multiples of 2, right? 2 times 1, 2 times 3, and so forth, are going to give you modulo 101 a negative 1. And all the even multiples will give you a positive 1. So that tells us that if we reduce any number, right, modulo 101, so we'll just copy this down, dot, 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 plus an 10 to the 2n, this is going to be congruent to, well, okay, a naught is just going to be a naught, but 10 squared becomes a minus 1, so we can just make this minus a1. Okay, what would be the next one? The a2 10 to the fourth. Well, 10 to the fourth is just 1, so this becomes plus a2, minus a3, and so forth. So you just keep alternating, okay? And well, of course, it depends. The very last one will either be a plus or a minus. So we'd have to write well, if n is odd, then we'll get a negative 1. So we'll have to put a minus 1 to the n here, times an. Okay, so what would that mean for our example, 34,862? So we would say 34,862, and this is of course modulo 101. I like to put it underneath sometimes. So this is going to be congruent, modulo 101 to, okay, you start from the end, 62 minus, okay, now you do 48 plus, okay, now we have a 3. Okay, 62 minus 48 is 14, plus 3 is 17. Okay, so this means that when you divide by 101, you get a remainder of 17, and so this number, 34,862, is not divisible by 101. Okay, so the way you're going to test divisibility by 101 is you break it up by pairs of digits, all right, starting from the constants, and you just do a plus, a minus, and then a plus, and if it's a multiple of 101, then your original number is divisible by 101. If otherwise, well, it's not, right? In fact, you even know what the remainder would be, right? If we divided 34,862 by 101, we would get 17. Okay, so what does that mean for our problem? Well, remember we know what our numbers look like, right? They look like a bunch of ones followed by a bunch of zeros. So what's going to happen when we pair these things off? So let's say we know it starts with 2 zeros on the end at least, right? So now I have some more zeros, and then I have a bunch of ones. And so this number is equal to some number of ones times, well, 10 to some power. Okay, who knows, 10 to the k maybe. Now, by Euclid's lemma, because 101 is prime, if 101 divides this number, a whole bunch of ones times 10 to the k, then it has to divide either the ones or the 10 to the k. Well, it definitely doesn't divide 10 to the k. 101 is not a divisor of 10 to the k because this just looks like products of 2's and 5's. Okay, so by Euclid's lemma, we know that 101 has to divide all of the ones. Cool. Well, we know how to test divisibility by 101. So I write down a bunch of these ones, right? And what am I going to do? Well, let's write some more ones. I'm going to pair them off, right? Starting from the end, and I give it a plus and a minus and a plus and a minus. And each time I do this, right, I'm getting 11 minus 11 plus 11 minus 11. And so at the very end of the day, like most of these are canceling out, right? So this gives me 0 and this gives me 0. At the end of the day, what are my options, right? I'm either going to end up getting, well, let's see. If this last one was a plus, right, then all of these were 0, and I ended up getting 11. Okay, that doesn't work. It's not divisible by 101. Or maybe there's another extra 1 here on the end. Okay, so that gives me a minus, and I would have 11 minus 1. Well, that's 10. Well, that doesn't work either. Okay, but what if I put another 1 here? Well, now I have 11 minus 11, that's 0, and that works. So the only way that I'm going to get a 0 out of this, right, which will tell me I have a multiple of 101, is if I have 4 ones in a row, right, at the very end of this line of ones. Okay, which just means, right, that I have groups of 4 all the way down. I have a multiple of 4 ones, right? So the number of ones must be a multiple of 4. Okay, so how many different ways can I do that? Well, we had one restriction we haven't used yet, which is it's a number at most 2020 digits long. So what can I do? I know I have to start with at least 2 zeros. Then I can have some number of zeros. And then I need to have a multiple of 4 ones. Okay, so what's the most I could possibly have in terms of multiples of 4? Well, 2020 is a multiple of 4, but I can't have that many ones because I need to have 2 zeros on the end. So the next lowest multiple of 4 would be 2016 ones. All right, so I can have 2016 ones. That's like the biggest I could possibly get. All right, so I can have 2016 of those followed by 2 zeros. Of course, there's nothing stopping us from putting in another 0, right? We're allowed to go up to 2020 digits, and we've only used up 2018. So we put in another digit. Well, now we have 2019. Well, we can put in another one. Okay, now we have 2020. So if we use 2016 consecutive ones, we can either have 2 zeros, 3 zeros, or 4 zeros on the end. So in total, that gives us 3 different possibilities for when we have 2016 different ones. Okay, well, what happens if we get rid of a set of 4, right? Remember, every time we get rid of some ones, it's got to come in a multiple of 4. So if we had 2012 of them, well, we know we have to have at least 2 zeros, but I can go up to 2020 digits, right? I have 8 zeros I can put up to put here potentially, right? So this could be up to 8. Now, of course, we know it's at least 2, right? There has to be at least 2 zeros. So there are going to be 7 different options here. Okay, of course, all that really did, right, was add 4 more options to what we could actually have because we got rid of 4 ones, which allows us to put in 4 zeros. So the next one, 2008 different ones, well, we're going to add 4 more potential zeros, so up to 12, which means we're going to have 11. Okay, and this is going to continue in this way. So how many are we going to have altogether, right? Well, at the very end here, we're going to have, well, we said we can't have no ones, right? That's not allowed, right? We need to have a positive integer. So the very last time we do it, right, that's when we have 4 ones, and then we'll have up to 2016 zeros, right? So up to 4 ones, right, and then up to 2016 zeros. And so we'd like to know, right, what this last number is. So a good way to see it is the following, right? 2016, we know that that's 4 times 504. And 2012 is 4 times 503. And 2008 is 4 times 502. And we keep going down, and this last one is 4 times 1. So we're counting. There's basically going to be 504 items in this list. Okay, so we're starting from 3 and we're adding 4 each time. So you could think of 3 as being 4 times 0 plus 3. And 7 is 4 times 1 plus 3. And 11 is 4 times 2 plus 3. Okay, so this very last one needs to be 4 times, well, okay, we're kind of offset by 1, right? There's going to be 504 things in the list, but we started our counting at 0. So this will be 4 times 503 plus 3. So if we wanted to know exactly what that number is, you say, okay, well, let's see. That's 500 times 4 is going to be 2,000. 2012 plus 3 is 2015. Okay, and oh, maybe we might have just noticed a little pattern anyway, right? So when there were 4 zeros at most, you got a 3. When there were 8, you got a 7, a 12, and 11. Oh, hey, look at that. It's one less. 2016 gives you 2015 possibilities, right? Again, corresponding, right, to you can choose any of these 2016 possibilities except for the one where you have only 1 zero, right? You need at least 2 zeros. Okay, so to solve this problem, we simply need to add up 3 plus 7 plus 11 plus dot 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 plus 2015. Okay, or if we use this notation on the right, we're basically going to be adding up things of the form 4k plus 3, where k goes from 0 through 503. Okay, now what I want to do is break this up just a little bit. First, it's a finite sum, so there's no problem breaking anything up. There's no issues with convergence or anything. So I'm going to break it up over this plus, and I'm going to pull the 4 out. So I get 4 times the sum from 0 to 503 of just k, plus the sum from 0 to 503 of 3. Okay, so we have 4 times, and this is the famous Gauss sum, right? You sum the first n numbers, and of course, when k is 0, there's nothing even to sum. So we're really summing from 1 to 503. And so in that case, we get we get 503 times the next number, 504, divided by 2. Okay, and then over here, you're just adding up 3 504 times. So that will be 3 times 504. All right, so okay, you get a little cancellation there, and so you get 503 times, okay, let's make that 1,008, and this is 1,512, and well, okay, this is just arithmetic at this point. So let me see, okay, that's 503,000. Okay, plus another 4,012, and then 5,520. Okay, so it looks like we get 508,536, right? Yeah, 24 and 12 is 36. Okay, I buy that. All right, so that looks like our answer to A1 from the 2020 Putnam exam.